All right, so um, today or this week, the pre-spring break week is sort of our last week of all things genetic. So then post-spring break, let me see if I can turn this tracking back on over here. Post-spring break, then the goal will be um, to then focus on alternative optimization meta-heuristics inspired by other aspects of natural systems, non-genetic, non-evolutionary, but still in many cases population-based, but not all. And then also transitioning to other sort of bio-inspired AI, like the sort of foundations of neural networks, where that comes from, the future of, and so on. So that's kind of where we're heading. So with that in mind, so today, I'm going to sort of finish up niching methods for multimodal, and then if we have time, then transition into that sort of post-spring break content. And then Thursday, Stephanie Forrest, who's sort of a distinguished faculty member here at ASU, who is one of the ones associated with developments in genetic programming, with an automated software repair in immunocomputing, particularly negative selection. She will be giving the guest lecture on Thursday. I want to make sure that she has a good reception. And so I appreciate those that taking advantage of the recorded lectures and so on. And so sometimes it's a little lonely in here, but that's fine. But for when she comes, given that it's sort of the singular event, I want to make sure she does have that good reception. So we're not going to record that lecture. But I also do want to make sure that there's extra incentive to be here for that. So I will put a little bit of that content on this sort of final exam that we'll have at the end of the semester. So there's, I think, reason to be here and reason to see her give that lecture. Her goal is to present on automated program repair and some of the connections to nature-inspired computing and how they led to useful applications and so on. And I know that from the muddiest points, there were a lot of questions about genetic programming and automated program repair and so on. And so she would be a great person to talk to as a practitioner in this space and really a thought leader in this space. And so I think it's really a privilege that she'll be here on Thursday. So I hope you're looking forward to that. So that's the plan for the rest of the week. And then that will wrap up all things kind of genetic for the semester. With that in mind, mini project 4 is due at the end of spring break. So not expecting you to do any more content reading, but just didn't make sense to make it due this weekend. So it's end of spring break as well as concept check 4. And then so we'll be then firmly in unit 5 coming back from spring break. All right, so any questions about that? Okay, so last time we finished off talking about how fitness, well, so basically niche preserving methods, niching methods, methods to establish niches, but not cluster too many individuals in those niches, and so spread them out with not destroying any niches that you've found before. So that's kind of the goal here, is that we have these methods that they can also just as well be applied to Pareto optimization. So once you've found that Pareto frontier, how you distribute among them. But they a lot of the development of these initially was for multimodal optimization, where the goal here is to put as if you have this optimization objective here that has lots and lots of little peaks and local optima. Whereas in a canonical GA, it would be okay to distribute your population just on, say, the highest peak, and then you could kind of pick the one that was the highest of that little subpopulation. Here, we really want to find all of the peaks, and we don't want a lot of noise. So the best multimodal solution will be one where you have individuals on every peak and you don't have a lot of spread on every peak. So when we talk about niches in single objective optimization, so this is our multimodal single objective. Here, so niches in multi-objective were different trade-offs. So if you had objectives 1, 2, and 3, there would be a niche where you just prioritize 1, a niche where you prioritize 2, a niche where you prioritize 3, and then a bunch of niches where you mix the prioritizations in different ways. And then if you would then want a portfolio of solutions across that niche space. In single objective, then each one of these acts kind of like a niche. And so the goal here, so this is another niche and so on. So we have two goals. We want to, one, find all niches. And then two, we want to sort of collapse, so coalesce or converge around the best solutions within a niche. So we want to, I'll say converge within a niche. And so this is a little bit like competitive exclusion in community ecology. And so the idea in ecological communities is that if you have a bunch of individuals that do the same thing, the ones that do it most efficiently are the ones that are going to produce more offspring. And so they're going to clear out any of the ones that look like them, and they'll just be the sort of sole representative of that niche. But if you have other niches, then one option for those strategies is to evolve into other strategies that take advantage of other niches. So we've presented that in multi-objective space as different trade-offs. So, there might be a ground niche, there might be an air niche, there might be a flower niche, there might be a carnivorous niche, et cetera, et cetera. But in single objective here, then each one of these peaks we view as a niche. So we're trying to converge within the niche, so converge in that direction, but then diverge, across the niches. So we're trying to do two things at once. And that's what these niche preserving or niching methods are trying to do is if you have a finite population, you don't want to waste a bunch of them in one peak. If you've got a bunch at the top of the peak, you'd like to keep the one that's closest to the top and fine tune it. And then anyone else that's nearby, send them elsewhere. So that's what we're trying to do with these niching methods. And so, and any questions about that? So I know there were some questions about niching and trying to understand that in the muddiest points, and hopefully in the comments helped with. Okay, so one of those methods that we introduced last time was fitness sharing. Where if we're basically, very similar genotypes, I guess I'll add very there, very similar genotypes with multiple realizations, or I'll say individuals, share fitness across their representatives. That's where the term comes from, representatives. So the idea here is that if you and another individual have almost the identical genotype, then it's sort of unfair for you to have that multiplicity. So if you have two individuals that are twins, if technically that genotype is really favorable, then if there were a lot of resources available, then both twins would have a lot of offspring. But here we're saying, no, we're effectively limiting the resources. And we're saying that you actually have to compete with your twin for limited resources, for limited fitness. You both have basically the same genotype. Rather than you both getting 8 offspring, we're going to give 8 offspring to the genotype, and you have to split it up between you because you're basically the same genotype, even though you have 2 copies in the population. So that's what we mean by fitness sharing. So, but then you have to decide, well, what is a sufficiently similar genotype? And that's where we got these kind of sharing radius around you, where you can say that anybody whose genotype is sufficiently similar to me, then my fitness is going to be divided down by the number of them, because effectively my strategies are duplicated in all of those around us. And so the genotype is an unfair advantage because there's a cluster of us all in one place. And that's what fitness sharing is trying to do. And then hopefully what happens is that one of them remains. So that's like the top of the hill here. And then all the rest of them get sent to other places of genotype space where they can explore other hills. That's the idea behind fitness sharing. And so a kind of generic way to do that is to say that, and this is just rehashing what we ended with last time, your shared fitness of individual I is going to be equal to their original fitness or their alone fitness, I guess, divided by some cluster size that I'll call the NCI, which is a count of nearby individuals, where we're going to generalize that to be a little softer. And so how do we define this count? So I'll just define F shared as this. Then that count, we're going to define as the sum of this sharing function that is based on the distance here. So this from I equals 1 to n for the number in the population. So this here is our sharing functions. Oh, and I'm sorry, this is j. Sharing function s dij of distance dij between I and j in genotype space. In other words, dij is just some distance, some norm of xi minus xj. And so typically we want this in genotype space, not function space. So that's how similar these two genotypes are. So if this is equal to 0, they're the same genotype. They're right on top of each other. If it's close to 0, there might be a few mutations difference, but for all we know functionally, they're very, very similar if they end up being on the same peak anyway. So we're going to effectively, this sharing function is just deciding how we're going to penalize very nearby genotypes, how we're going to count them. So the simplest thing to do would be just to make this a 1 if you're sufficiently close and a 0 otherwise. But we can soften that so that, and that's what I'm about to write here for this function, so that we have sort of a continuous penalty that is closest at 0 distance and gets lower and lower and lower at infinite distance, but maybe never falls to 0. Now, why would you want to do that? That will make it so that if you have on the first round of this kind of spreading out, you might get a clump all at one point. And then suddenly that will that'll have a huge fitness penalty, and that will then spread out a bunch of them all over the space. Well, that's good. But then now that they're spread out, by having this sort of skirt which goes off into infinity, then it further allows us to kind of optimize the spread to try to say that, well, if I have an individual that doesn't have any nearby but has a few kind of close, but at arm's length or just beyond arm's length, versus an individual who has a lot of space around them, then I might prefer to spread out the individual that has a few closer neighbors. I mean, ideally, what I'd like to get is if it's possible to sort of uniformly spread all of my individuals. And of course, they have to be modulated by the fitness peaks. But if it's possible to spread them out so that there's no clusters at any length scale, that's what I'd like to do. And so by creating a sharing function, which has this kind of infinite skirt, then it potentially allows for this continued spreading so that it doesn't just penalize nearby and then stop. So, well, that's a parameter that you can play with. And so we define the sharing function S of the distance between I and J as we're going to say, 1 minus, and then I can define dij over sigma share. So I still have a sharing radius that I can play with to the alpha. And that's if the distance is less than sigma share. So you could potentially make this sigma share very, very large. That's kind of the skirt going off to infinity. And then this alpha is another hyperparameter that you have to play with. So, and then 0 otherwise. And so we see here that if, how do I want to write this? So if alpha is equal to 0, then it doesn't really matter what's in here. This will be equal to 0. And so at that point, you've got, no penalty. If alpha is equal to infinity, then you've got, regardless of what this is, because this is all going to be less than 1, then the infinity, the less than 1 raised to infinity, this is going to go to 0. So then you've got the pure 1 count here. So so that's, for alpha equal to infinity, that gives you count. It's a pure count within sigma share. But then as alpha goes to 0, then you've got kind of a soft count based on distance. So of course, when alpha is all the way to 0, then you get no count. But if alpha is somewhere in between 0 and infinity, then you get this sensitivity to distance, where if the distance is 0, you get the full count. If the distance is slightly bigger than 0, then you get a little less of a count. Slightly bigger than that, a little less of a count, until eventually it hits sigma share, and then it goes to 0, and then it falls off to 0 for everything outside of sigma share. So this gives you a way to sort of soften that so that it's not quite this sort of hard count here. But implementing this, so of course, if you want to set alpha equal to infinity, that's basically you're just going to get rid of this. You're not going to implement the infinity. But that's kind of the sort of conceptual model here is the alpha equal to infinity, where it's just a count when you're inside and not count when you're outside. So that's fitness sharing. Does that make sense? So who's sharing the fitness? It's the genotype that's sharing the fitness. And so it is possible that if you have just the right spacing, that maybe like you're going to have, it might be that I have a bunch of similar genotypes close to me, and so I'm going to get penalized by 8. But the one over here, those genotypes aren't within its sigma share. So even though I got penalized 8, one of my neighbors that caused me to get penalized 8 might only get penalized by 6, and one of its neighbors might only get penalized by 4. So it's a little weird to call it sharing because you're not allocating the same fitness to all individuals in the cluster in this approach, but it does sort of have that same essence where the idea is you're going to try to penalize clusters with more individuals more than you penalize clusters with fewer individuals. And this approach shows up not only in multimodal, but also in multi-objective. But it's sort of, I think a lot of the development of these approaches really were inspired by thinking about multimodal. Okay, so that's fitness sharing. Alternatively, um, so we have to then think about like how fast is this going to be? And we're going to have sort of a list of these things. But as you look through these things, just try to think if I wanted to implement this myself manually, how annoying would this have to be? I mean, I'm going to have to calculate these pairwise distances every time I move something around. If I'm smart, maybe I can save those pairwise distances into a table and I just update that table whenever I move one. And then, if I move one individual, I just update all the distances that correspond to that one individual. And then maybe I don't have to recalculate the same distances over and over and over again. Maybe that's one way to optimize that. But that idea that I have to calculate, every pair in a network, that gives you this sort of n squared type of feel. So if you're talking about doing lots and lots of generations of a GA, these computational costs can add up. So, we might consider other ways to do something similar. So there are clustering approaches as well. So, this is fitness sharing by clustering. And this is good old-fashioned AI, clustering. So this is inspired by, k-means clustering. And so the idea here is that what might be faster for a large number of individuals is to define some parameter k that again, it's going to relate to this kind of k-means idea, but where I'm going to use, say, I'm assuming there are k seeds for clusters out there. And I'm going to start out by saying, find the best k seeds, I'm going to sort all the individuals by fitness, and then take the top k individuals in fitness. And then from that top k individuals, then I'm going to get rid of the closest individuals around them. And then I'm going to repeat this process until I've gone through all of the individuals. And every time what I mean by remove, I'm going to set their fitness to 0 so that at the next iteration through the genetic algorithm, then selection will move them out and then generate new ones via mutation. So to write that down, then I have my in individuals. So sort in individuals by fitness, and then consider the k best, and then take k best individuals as seeds for clusters. So we know they're the best, so we want to keep them around. So these are sort of like centroids. And then from there, we're going to use another two parameters, dmin and dmax. We've got parameters dmin and dmax. And these are going to define how we're going to clear out the space around each one of these cluster seeds. So basically, we want to make sure that I might have actually said this a little bit backwards here, but ideally, we would like to make sure that our cluster centers have, how to say this? So our cluster centers, we want to be no closer than d min, but we want individuals and their centroids to be no farther away than d max. Say that right? So in our genotypic decision space, we want d min between cluster centers, and then between individuals and their centroids, D max. So write that down. We want D min between cluster centroids, or seeds, and we want D max is, I'll say, and that's a minimum. And you want D max between individuals and their centroids. And that's a maximum. And so there are going to be individuals that are too far away from any cluster, and there's going to be cluster centroids that are too close to other clusters. So we can use these to decide which individuals to adjust their fitness. So the idea here is we can say, like, we can create a new shared fitness, which is going to create a different type of cluster count, but it's inspired by the approach we just did. So we still have F original that we're dividing down, but then we're going to take NC, which I'll write this down here, but this is the number of individuals in this cluster. And we're going to multiply that by this scalar 1 minus DIC. So that's the distance between this individual and its cluster center, divided by 2D max. And then we're going to raise that to the alpha, just like from before. So we have DIC, that's distance between I and cluster center, or a cluster centroid in our genotype space. And what's nice about this is that having this can be calculated once per cluster. So this is an attempt to try to reduce all the pairwise calculations, is that if you can establish these centroids, then you can count all the individuals in the centroids and then use this count for every individual in that centroid. So then you don't have to calculate all of these pairwise distances. You only need to know the distance of all the individuals in the cluster with that centroid of that cluster. And so based on how far apart they are, then the ones that are very close to the cluster center will end up getting a significant penalty on their fitness. The ones that are hanging out towards the edge of the cluster will get less of a penalty. So that's the idea here, is that we're trying to create, so this here is trying to create, this creates clusters that are spread out. And then this D max here adjusts penalties within the cluster. And then hopefully this is more efficient to calculate. than uh, full pairwise pairing. So this is, again, just an attempt to try to make this a little less computationally costly. It just makes it a little more difficult to conceptualize. But and on top of that, then you also want to do this. You want to repeat this until each one of these have been, and I just want to make sure I'm not misquoting here, because in my memory, you repeat this until you actually do this for, actually, I think I'm mixing that with that. So that's all I want to say about that. So this is the algorithm here. You come up with the k best individuals. You If there are two individuals that are too close together, then you look for another individual so that eventually you get the k best individuals that are separated by d min. Once you have those k best individuals, you then see who's in their fiefdom of individuals that are within d max. For each one of those individuals that are within D max, you scale them by their original fitness by the total number of individuals in that little fiefdom. They're kind of sisters in that kingdom. And then multiply that here by the scaling function, which has to do with how far they are from the center. So if they're hanging out on the very edge of this cluster, then they won't get much of a penalty. Because this will scale down this count. If they're hanging out very close to the cluster center, then they'll get the full penalty of all the individuals in that cluster. So it does the same thing as our pairwise clustering from the previous slide, but it hopefully does it at a less computational cost. Yeah. Yes, these are parameters, hyperparameters. I'll say H parameters. Likewise, this is also a hyperparameter. And so is this. Yeah. That's the idea, is that you hopefully you have sort of a baseline level of these that for many different optimization objectives will work okay. But if you're noticing that you run a couple of pilot runs and you're just not getting a lot of diversity, then the idea here is you can say, well, I want more clusters. So that's going to create more of these little centroids around. I want to make sure that these clusters have more space in between them. And so then that will help sort of spread them out a little bit more. I might want to make the space between the clusters different. So it gives you the ability to sort of try to figure out how big your niches are. And then so once you sort of establish the size of your niche, then theoretically this will make it so that those inside the niche, inside the cluster, will end up only one, like only a few will survive. But then if you have a lot of niches, then you should hopefully get individuals that show up in all of the other niches and spread them out. So yeah, these levers you get the opportunity to kind of toy with. And unfortunately, with any meta heuristic, you often have to run pilot runs to kind of see how well it's doing and then adjust the parameters to kind of see if, well, okay, now it looks like it's starting to spread out through the whole space. And then you can let it rip with, larger numbers of individuals and more computational budget and so on. And termination conditions, that also came up in the muddiest points. So things get hairy with termination conditions, especially for multi-objective. So like in multi-objective, you can say, well, how do I terminate? The easiest termination condition at this level in your career to think about is just number of iterations or computational budget. So if you've got, you can say, I only got enough computational budget to run my run 500 executions of these costly optimization objectives. So you just stop after you hit 500. Now, more sophisticated multi-objective functions have ways of convergence that actually use all of, like, convergence is easy to imagine when you have one objective. It's like I haven't seen an improvement in my one objective in 10 generations. I've converged. When you have multiple objectives, it's a little more complicated because there's a bunch of different degrees of freedom you can observe. So there are these hypervolume approaches to convergence where you sort of look at like, can I put a volume around my optimization objectives and then ask, has that volume moved very much? And that's kind of the sort of convergence idea. Like, has my Pareto frontier changed? Has the sort of envelope around my Pareto frontier changed very much? That sort of can become a convergence condition for these multi-objective. But that's kind of outside of the scope of the things that I want to cover. They're kind of like technical details. So for these sorts of things, if you need a convergence condition, just imagine that time or number of generations, that's an easy convergence condition that you can always use that. There are more sophisticated ones. It's the same thing with multimodal, because you don't have, you're not just looking for the best improvement in fitness, you also want the best spread. So you can say, like, can I can just stop after 100 generations? Or I could say that, I haven't found a new fitness peak in the last 10 generations. So maybe then, it's time for me to stop. I'm not gonna find any more niches. And hopefully I've got such high selective pressure within my niches that I don't need to iterate very much to find the top of each individual niche. So that's, a way that we can handle, termination conditions. All right, so I'm sure I've probably kind of confused things a little bit, but hopefully, you know, maybe the order in which I presented these things wasn't ideal or optimal here, but hopefully it's pretty clear that you look for the best individuals, you try to find, hopefully, you've happened to just randomly find the K best peaks, and they're all the top fitness peaks in your multimodal optimization. But if you happen to get a couple that are on the same fitness peak, then they're not going to meet the D-min criteria. And so you could find a new cluster center, the next in your list. So you then eventually you find K cluster centers that are separated by D-min. And then after that, you use D-max around them to penalize the individuals that are peppered around each cluster center. That's the idea behind this kind of clustering-based fitness sharing. Questions about that? And the goal, again, is for computational efficiency. All right, so clustering, I guess I'd say fitness sharing, that is one major way to do niche preservation. So, just to highlight fitness sharing. Clearing is the other half of it. So fitness sharing is a way to sort of subtly reduce the fitness of individuals that are close by so that hopefully you encourage the genetic algorithm to not promote all of them simultaneously. Another approach to that, which is often used in concert, is clearing. And clearing is basically a way to supply resources only to um, the best. So it's sort of like an elitism within the niche. So I just referred to having high selective pressure within niches. And so here I'm sort of saying, like, well, let's take that to the extreme. Well, so the once you found the best within a niche, just get rid of everybody else in the niche. So this is sort of an extreme version of fitness sharing where you have like maximize up the kind of fitness pressure. So the idea here is that we're going to sort by fitness. And we're going to start similar to the clustering method and take the K, and that's another hyperparameter, best solutions. All right, so then kind of an extreme version of fitness sharing, we're just going to see who's around there, who's around those best solutions, and we're not even going to give them a chance. We're just going to clear them. So we find all solutions within sigma clear, that's another hyperparameter, of each of the k, and set fitness equal to 0. And that will cause them on the next generation to be cleared out by the selective operator. So if their fitness is equal to 0, they're just going to have 0 offspring. So then they are going to be replaced by mutation, basically. So this will force replacement. And then we repeat um, for next k best until all considered. So this clearing-based approach, again, this is like super high selective pressure, where you're just going to say, all right, who are the best out there? I'm assuming you're the peaks. Okay, let's put a circle around all you. Anyone within those circles, you're dead. And you're effectively going to get redrawn randomly somewhere else in the population. So if you're unlucky enough to be near one of the K best, then your fitness goes to 0, your genotype does not carry on. And then we look at the next K best. We do the same thing. And the next K best, we do the same thing. So after the end of this, a subset of the population gets their fitness equal to 0, and they effectively get replaced. And they can be replaced by, totally random mutation. So basically reinitialized. They can get replaced by recombination of the others here. But I mean, the point is that that genotype that was nearby, it does not survive. It doesn't even have a chance of surviving. It just gets replaced. So that's the basic idea behind clearing. And then there are modifications of clearing. So for example, we can do modified clearing, where we're a little more conditional about things. So in modified clearing, then we we still start kind of the same way, where we've got an individual that we're interested in who's around that individual. But we now have different spheres that inside that sphere, we treat individuals slightly differently. So if you're super close to the individual, that's bad. And so if you're within, I'll just draw a little circle here. Maybe I'll actually try to make that a circle. All right, so I got my center of the circle, got something circle-ish. And so I've got some radius r. And so if you're another individual within radius r, you're going to be cleared. So that's just like above. So you will be cleared. Clear within radius r. But what if you're just outside of radius r? Well, we're saying that we don't want to necessarily clear you, but you're a little too close for comfort. So maybe we just like to move you. So we're going to create another radius outside of that radius r that's, say, 1.5 r away. So we'll call this 1.5 r. And then we're going to create a third sphere of optimization hell Sorry that that's not quite concentric. Hopefully that is enough to make the point. That I'm going to put 3R away. And basically, if you're found here in this 1.5R space, we're going to move you into this new location. So move those between R and 1.5R to space between 1.5R and 3R. And so this is an approach that was introduced by Singh and Deb, 2006, as an example of modified clearing. And and that's basically it. So it's just a slightly different version of what we have above, but we have this kind of this additional region where we just add a little bit of a direction that is away from our cluster center here, and we just push them away. So we don't adjust their fitness directly. We don't just clear it, set it to 0, but we do mutate them in sort of a directed way. So you could think of this as a type of directed mutation. And then you can think of this as a total random reinitialization. All right, and that's modified clearing. So, I'm not going to ask you like a bunch of the details here. The big thing is I want you to know that clearing approaches basically just zero out fitness when you're sufficiently close. And there are alternative ways to do that where, just like in fitness pairing approaches, you can create this soft boundary, which still penalizes those that are far enough away to sort of be manageable, but still it'd be nicer if they were a little farther away. That's kind of what this modified clearing is attempting to do. And it's just this attempt to try to discover all the niches, but then also make sure you don't have multiple representations within the niches. Are there any questions about the clearing approaches? Okay. And then the last option that I want to mention that's popular are approaches based on crowding and so-called restricted tournament selection or modified tournament selection approaches. So we've already know about tournament selection. And so tournament selection can be co-opted for this kind of niche preservation. But you have to be very careful because tournament selection can very quickly totally delete a niche if you're not careful about how to do it. So crowding and restricted tournament selection. And on that, the the comprehension or check, I think the second one, 3B, you had some exposure to these ideas of restricted tournament selection in that paper that I had you take a look at. So this is again based on a kind of a competitive exclusion idea that individuals too similar to others in their niche will not be able to find enough resources to persist. So the idea here is that we are going to directly compete individuals versus other individuals when they're very similar to each other and only keep the ones that are best among those individuals. So, and again, it's sort of similar to these clearing approaches, but we're doing it on a kind of a little bit more of a pairwise procedure here. So, um, the we can do crowding based on parent offspring conflict, or a similarity. So I'll say competition. So here we're under the assumption that offspring will be very similar in genotype space as their parents. And so we are going to directly compare parent and offspring and only keep the best ones. Now, two parents cross over and produce two offspring. Those two offspring, what we have to do first is sort of see which parent are they most similar to. And so it might be that daughter is actually more similar to dad and son is more similar to mom. And then once you figure out who the pairs are, you compete them against each other and then keep the best one. And this is in the hope of not creating multiple representatives within a niche. So the idea here is that you select two parents from your population. So I'll call them P1 and P2. And we are going to do this without replacement. So without replacement. So other times when we've talked about crossover, we've said you can grab two parents out, you have the mate, you can put them back, and then you might grab those same parents again. Here, for the purposes of niche preservation, we're gonna do like we're just gonna march through the breeding pool and grab two parents at random, do this procedure to them, and then they're done breeding. And then we grab two other breeders, we grab two other breeders, and so on. So that's what I mean by without replacement. So then we do crossover. So our P1 and P2 become offspring C1 and C2. So those are our crossover versions. So we, pick crossover points, mix, an output. You get one mixture and then another mixture. Just the two complementary mixtures. And then from there, we can mutate them. So we have our C1 and C2 unmutated, and then they become C1 prime and C2 prime, are mutated versions. So there, now we can do tournament selection where we basically need to see who's most similar. So I could write this out in terms of a distance metric. Like I can say, like in my notes, for example, but I think it's going to be ugly. It's probably easier for me to write this some other way, um, but I basically can say, if P1 and C1 prime and P2 and C2 prime are most similar. So what I mean by that is, and this is what I didn't want to take the time to write out, but if the distance in genotype space, so whatever your distance metric is, if the distance between P1 and C1 prime plus the distance between P2 and C2 prime is less than or equal to the other pairing, i.e. the distance between P1 and C2 prime and P2 and C1 prime, then we're going to assume that P1 and C1 and P2 and C2, those are the ones that should be paired. Otherwise, we would pair P1 and C2 and C1 prime and P2. So I could write all that out, if dist these plus dist these is less than dist these plus dist these, then I'm in one case. Otherwise, I'm in the other case. So that's what I'm sort of trying to write in shorthand here, rather than getting tied up in that notation. And then the idea here is if the fitness of P1 is greater than or equal to the fitness of C1 prime, then use P1. Otherwise, use C1 prime. And then likewise, if the fitness of P2 is greater than or equal to the fitness of C2 prime, use P2. Otherwise, use C2 prime. So we are taking two parents, creating two offspring, figuring out which offspring is most similar genetically to which parent, and then in those two pairings, picking only the best. So it is a form of tournament selection between parents and offspring. So in the end, this results in two individuals instead of four. So then, the otherwise case is that we would then compare P1 to C2 prime. So if P1 is greater than or equal to F C2 prime, similar, and then or if F of P2 is greater than or equal to F of C1 prime, similar. So this is like a tournament selection, tournament between parents and offspring. Okay, questions about that? About what I mean here about, finding in this case, these two are most similar, these two are most similar, so we pair these two together and these two together. So we're just pairing up by similarity, pair by similarity. All right, so that is crowding based on parent-offspring conflict. The problem with that is you can accidentally completely delete a niche with this approach. So how might that happen is that it might be that parent one is the only individual representing one particular mode of our multimodal function. And it might be that offspring C1, who's most similar to parent P1, is actually due to crossover with offspring P2. So maybe I could draw this out here. So if I were to have a situation like this, I don't know, something like that, then I might have that this is parent one, and this right here is parent two. And it might be that this ends up being, and maybe I should make these a little bigger. Sorry, let me undo that stroke erase there. And so let's say I actually want to make these peaks a little taller. All right, so it might be that I've got these two parents, P1 and P2. After they recombine, then they sort of average in my decision space, and I end up getting offspring that are intermediate, like C1 and C2 right here. So here now, it would be great if I would have just kept all of these. Now, I was worried that C1 and C2 would land in the same peak as P1 or the same peak as P2. So I do this algorithmic approach to try to create a little tournament to say, all right, I only want to keep the best in every mode. But due to crossover or due to maybe extreme mutation, there is a chance I'm going to actually find a new mode with one of my offspring. That's great. But what's going to happen here is that if I compete these two against each other, so if I do tournament here, this is by the primes. So tournament between these will kill P1 peak. And so we lose a niche. So the tournament here will end up killing this whole niche because I've ended up pairing up these two together. And that's exactly the opposite of that. So it's true that I've discovered, so here we've discovered new niches, which if I was doing a canonical GA, that'd be great. I can get rid of the local optima because I found things that are more likely to be the global optima. But if I'm doing multimodal, I don't want to get rid of any of my local optima because I'm trying to collect all of them. So this here, this basically is that local gets killed on discovery of global. And so this is a downside to using this parent offspring. It's convenient though, because you know that the parents, you don't have to figure out what other individual to use a tournament with the parents. You just immediately, like, this is just convenient to pick the offspring, because most of the time offspring are probably going to be in the same mode as the parent. But if you happen to pick two parents that are very far away from each other, crossover could create intermediate offspring that are on completely different peaks. So that could be a problem. Questions about that? Does that make sense what I mean by niche loss here? So one way to deal with this is to not use tournament selection in this particular case, but to actually use something a little bit more like fitness proportion selection. So basically probabilistic crowding. So one solution is probabilistic crowding. And so in that case, we basically say replace with probability f of x, whoever x is, divided by f of x plus f of y. So this is basically fitness proportionate selection in a pair. So that at least provides some probability that niche isn't lost. But it also means that maybe the new niche that we just found isn't found. So this is not ideal either, but it at least softens the blow a little bit. So really, the the best kind of approach to that. So this is, so I'll say, but new niche isn't found. So, a response to this is so-called restricted tournament selection. So that'll be what we will probably close here. So restricted tournament selection, or RTS, is the idea that why should we limit the tournaments between parents and offspring? Let's just go through a potentially costly computational search and figure out who really is the best individual to pair up with every newly generated individual. And those hopefully will be the ones that are right next to each other on the same fitness peak, so that I can do this kind of clearing action. Now, I may not want to do all pairwise combinations, so maybe by restricted tournament selection, I randomly select a subset of individuals in my population to do tournaments with my new individuals. And that's basically the idea here. So I'm going to have parents, AB, that produce offspring, A prime and B prime. And instead of competing the parents together, so these are our parents and these are our offspring, instead of comparing parents to offspring, I am going to say, all right, these are my new offspring. I want to see, did these show up next to an existing genotype? If they did, just use the best one. But if they're far from an existing genotype and maybe they're in their new niche, maybe we leave them alone. But I want to do that in a computationally efficient way. So we're going to find individuals in a population window W which are selected randomly. So this is drawn at random. So you as a hyperparameter can pick how big this window is. So rather than looking at all of your 100 individuals and trying to say which of the 100 individuals is each one most similar to, we're going to say, well, pick 20 individuals out of my 100 or pick 20% of my population. Draw a random subset of those 20% and then compare the individuals to that random subset. And then this individual will then be most similar to, in this case, I'm focusing on A prime, our new offspring A prime. And we're going to call that A double prime. This individual this individual we're going to call A double prime. They are the individual in the random subset of the population that's most similar to that offspring. And then we can do tournament selection on those two. So keep A prime or A based on tournament selection. And this hopefully should prevent tournament selection between peaks. So this should, hopefully prevent tournament selection between peaks and limit it to TS within peaks, a peak. That's kind of the idea there. So when you hear about RTS, that's kind of what they're shooting for here. Okay, any questions about that? All right, so after spring break, we'll start on, that's basically, so there's this one page that I just want to sort of summarize computational complexity. I'll probably start with that just after spring break, but it basically says, I can just share it with you now, fitness sharing is in squared complexity, clearing is linear complexity, RTS is linear times the size of that window, clustering is almost squared. Modified clearing is like a major, it's a really complex. So basically all of these different approaches people have gone through, and you can calculate the computational complexity of them. And what we end up finding is that RTS is a really nice balance. Especially if you make this window size, if you can manage to make it significantly smaller than your total population size. If you make it your whole population size, it's in squared complexity. But if you make it, 10% of that, then it's actually a pretty good balance. So RTS ends up being very popular in these approaches. It's a good balance of all of these different things. Does it work the best? No. But if you want your GA to actually finish, to reach those termination conditions, then it's not a bad one to use. And that's kind of where I'll spend 5 minutes on before we then go into entropy and simulated annealing for after spring break. So, but Thursday, Stephanie Forrest, be here. It'll be great. A lot of good questions I hope you bring to her. And it should be a real treat. That's all I've got for you. So have a good day.